If I were to ask you about the most luminous star in our night sky, your answer would likely be Sirius. And if I followed up by asking for the closest star to us, besides our Sun, you would probably name Proxima Centauri. This presents a fascinating puzzle that has captured my curiosity for years. Why is this star, our closest celestial neighbor at a mere 4.2 light-years, entirely hidden from our unaided vision? By all logic, a star so near should stand out as a brilliant point of light, yet it remains shrouded in darkness. The enigma of Proxima Centauri isn't merely about its faintness or its proximity. It serves as a gateway to understanding the fundamental processes of stellar evolution, planetary formation, and the harsh realities of worlds that exist just beyond our own. What truths are concealed in this nearby patch of cosmic shadow? And what pivotal secret does this unseen star guard? A secret that is at once an invitation and a cautionary tale. Join me as we venture into this subject to reveal what lies beneath the surface. To properly investigate our unseen target, we must first examine its cosmic environment, as Proxima Centauri is not an isolated star, but a member of the renowned triple-star system, Alpha Centauri. Grasping the peculiar nature of this dim companion requires us to first acknowledge the magnificent presence of its two brighter partners. From the perspective of the Northern Hemisphere, this system is largely theoretical, a name in textbooks, concealed from view beneath the horizon. However, should you travel to southern locations like Australia or Chile, the view transforms dramatically, revealing the system as a brilliant gem set against the deep canvas of the night. There, alongside the nearby star Beta Centauri, it serves as a navigational pointer to the iconic Southern Cross, a role it has played for ancient mariners and explorers for centuries. Historically, Arab astronomers named it Rigil Kentaurus, which translates to the Centaur's Foot, marking its place within the mythological constellation. When you look up at Alpha Centauri without a telescope, it presents itself as one exceptionally luminous star, ranking as the third most brilliant object in the night sky, surpassed only by Sirius and Canopus. The star emits a stable, serene, yellowish-white glow, strikingly reminiscent of our own Sun, a similarity that, as we will discover, is far from superficial. For ages, humanity perceived this as a lone point of light, but a monumental shift in our cosmic perspective occurred when we accepted the profound truth that our vision alone is limited. The journey to understand Alpha Centauri's true composition began in 1752, when the French astronomer Nicolas Louis de Lacaille, observing from the Cape of Good Hope, pointed his telescope at it and was the first to resolve the single bright point into two distinct, closely orbiting disks of light. This finding, that stars frequently exist in pairs or larger groups, marked a pivotal moment in astronomy, suggesting that our solitary sun might represent a less common arrangement in the cosmos. It became clear that the galaxy is teeming with such stellar families, all interconnected by the unseen forces of gravity. These newly identified components were designated Alpha Centauri A and Alpha Centauri B, and it is crucial we become familiar with them, as their properties are central to the entire system's dynamics. Let's start our examination with the system's principal star, Alpha Centauri A, which would be a prime candidate if you were searching the cosmos for a twin to our own Sun. Its astronomical designation is G2V, a technical label that actually provides a wealth of information about its characteristics. The letter G classifies it as a yellow dwarf with a surface temperature around 5,790 kelvins, almost a perfect match for the Sun, while the Roman numeral 5 confirms it's a main sequence star currently fusing hydrogen into helium in its core, placing it in the most stable phase of its existence. In terms of its physical properties, Alpha Centauri A is marginally heavier than our Sun, possessing a mass of approximately 1.1 solar masses. And it is also bigger, with a radius 1.223 times that of the Sun. Consequently, it is more luminous, radiating about 1.5 times the total energy of our star. To use an analogy, you could think of Alpha Centauri A as the Sun's bigger, more powerful older sibling. Remarkably similar, yet distinct in its own right. Next, let's direct our attention to its partner, Alpha Centauri B, which is classified as a K1b star. The letter K identifies it as an orange dwarf, a category of stars that are cooler and less radiant than G-class yellow dwarfs. With its surface temperature measuring around 5,260 kelvins, it is both smaller and less massive than its companion, having about 90% of the Sun's mass and 86% of its radius, which causes it to emit significantly less light, only about half the Sun's luminosity. Following our earlier comparison, Alpha Centauri B could be seen as the smaller, more reserved younger sibling in this stellar duo. This pair, a yellow-white star and its orange partner, are engaged in a perpetual celestial ballet, bound together by gravity as they orbit a mutual center of mass known as the barycenter. You can visualize this like two dancers of unequal size spinning together. Their pivot point will naturally be nearer to the heavier individual. Similarly, the barycenter for Alpha Centauri A and B lies closer to the more massive star A, and their orbital period is immense, requiring 79.91 Earth years to complete a single revolution. Just think about that. One full year in their system is equivalent to an entire human lifespan here. The two stars follow a highly eccentric path, which means their separation is always in flux. At their closest point, a position known as periastron, they are separated by just 11.2 astronomical units, roughly the distance between our Sun and Saturn. When they reach their most distant point, or apoastron, they drift apart to 35.6 astronomical units, a gap wider than the orbit of Neptune or even Pluto. This constant movement establishes an environment of incredible complexity. Let's engage in a brief thought experiment to fully appreciate the magnitude of this scenario. Imagine that one of these stars, let's say Alpha Centauri A, hosts a planet similar to our own at a life-friendly distance. What would you see looking up from its surface? For starters, your sky would feature two suns. One would be the planet's home star, nearly identical to our own Sun, while the other, Alpha Centauri B, would appear as a star of unparalleled brilliance, unlike anything visible in our own night sky. Over the course of its 80-year cycle, the apparent brightness of this second sun would shift dramatically. At its most distant, it would shine with a magnitude of about -6, far outshining our full moon, which has a magnitude of around -13. But at its closest approach, its intensity would surge to -2, making it thousands of times brighter than the moon. It would appear as a stunning orange diamond in the heavens, bright enough to cast its own distinct shadows during daylight hours. The light bathing such a world would never be a simple white or yellow, but a constantly shifting fusion of yellow-white light from star A and orange light from star B. The sunrises and sunsets would be stunning beyond imagination. There would be times when both suns would set in unison, painting the sky with intricate shades of peach and gold. At other times, one star would dip below the horizon while the other remained high, creating a prolonged state of twilight that would take the place of true night. On a planet like this, the seasons would be governed by more than just the tilt of its axis. They would be profoundly shaped by the 80-year cycle of the two stars drawing closer and moving apart. When the stars were nearest, the planet would be bathed in substantially more heat, likely creating what you could call global orbital summers. As they moved to their farthest points, a period of planetary cooling would follow. Any life that managed to emerge there would have to be adapted to these extended, generational cycles of climate change. This is the breathtaking, elaborate, and ever-changing reality revealed by what appears to us as a single bright point in the constellation Centaurus. Two immense stars, almost twins of our Sun, locked in a gravitational dance for all time. For nearly 2 centuries after Lacaille's discovery, astronomers were confident this picture was complete, that Alpha Centauri was a classic binary star system, brilliant, beautiful, and fully understood. The universe, however, is rarely so straightforward, and hidden within this apparently finished story was a third, undiscovered chapter. The truth began to emerge when astronomers developed the ability to measure the movement of stars with exceptional precision, revealing something peculiar. The entire Alpha Centauri A and B system journeys through the galaxy as a single, cohesive unit, a phenomenon called proper motion. You can visualize this by picturing a distant flock of birds, all moving in roughly the same direction at the same speed. This principle suggested that astronomers should search for any other stars, however faint, that shared the exact same motion as this luminous pair. Lurking in the deep shadows on the system's periphery, far from the splendor of the 2 main suns, was a third companion. It is the nature of this star, its faintness, and its secrets that I want to explore with you today. Why, in a system so full of light, does a realm of near absolute darkness also exist? To find the answer, you and I must journey away from the system's bright core and travel to its cold and distant outer reaches. For many decades, the brilliant pair of Alpha Centauri A and B was a source of admiration and intense study, seen as a self-contained and complete picture of our immediate stellar neighborhood. But by the early 20th century, scientific instruments had become refined enough to detect subtle details that had escaped previous generations. One of these details was the proper motion of stars, their gradual but quantifiable drift against the backdrop of distant galaxies, which showed that stars within the same gravitational system ought to travel through space together, like a fleet of ships. This method soon resulted in a remarkable discovery. In 1915, the Scottish astronomer Robert Thorban Ayton Innes, serving as the director of the Union Observatory in Johannesburg, South Africa, was immersed in a painstaking task. He was using a technique known as blink comparison, which involves comparing photographic plates of the same region of sky taken years apart to spot objects that have moved. He noticed an incredibly faint star that seemed unremarkable, but upon tracking its position through the years, he realized it was moving at the same speed and in the same direction as the dazzling Alpha Centauri system. This could not have been a mere coincidence, as the probability of 2 unrelated stars at different distances from us sharing an identical proper motion is almost 0. Innes knew he had located the long-sought-after third member of the system. He chose to name it Proxima Centauri, using the Latin word proxima, which means nearest, a fitting name for our closest neighbor in space. Further measurements have since confirmed that because of its position in a vast, elongated orbit around the central pair, this tiny star is at this moment slightly closer to Earth than its much brighter companions. It stands as our forward outpost, our nearest neighbor in the vast cosmic ocean. And yet, its finding failed to create the kind of sensation that accompanies the discovery of a new planet. The reception was quiet and academic, primarily because Proxima Centauri bears no resemblance to its brilliant sister stars. It belongs to a completely different category of star, a class that populates the galaxy in vast numbers but stays almost entirely hidden from our sight, as Proxima Centauri is a red dwarf. To grasp what this classification signifies, we need to explore the fundamentals of astronomy. Stars are categorized into spectral classes using the letters O, B, A, F, G, K, and M. This sequence ranges from the hottest, most massive, and brightest blue giants of class O down to the coolest, smallest, and dimmest red dwarfs of class M. Our own Sun is a G-type star, a yellow dwarf situated somewhere in the middle, while Alpha Centauri A is also a G-type, and Alpha Centauri B is a slightly cooler K-type star. Proxima Centauri, in stark contrast, is classified as an M5.5 VE star, which places it very near the bottom of this entire scale. Let's break down what these symbols mean in simpler terms. The letter M indicates that this is an exceptionally cool star, with a surface temperature of only about 3,242 degrees Fahrenheit, kelvins, making it more than twice as cool as the Sun. This low temperature causes it to radiate most of its energy in the red and infrared portions of the spectrum, which is the origin of the name red dwarf. The letter E in its classification points to it being a flare star, which means its spectrum shows emission lines, a sign of the turbulent nature we will examine later. For the moment, the critical detail is that it is a dwarf, and this term is not an overstatement, as Proxima Centauri's dimensions and mass are genuinely modest. Its mass is only about 12% of the Sun's, or to be more precise, 1.23 solar masses, which places it very near the theoretical minimum mass required for a celestial body to be a star. If it were just 1/3 lighter, the pressure and heat in its core would be insufficient to sustain stable hydrogen fusion. In that case, it wouldn't be a star at all, but a brown dwarf, a failed star that glows faintly, only from the energy of its slow gravitational contraction. Proxima Centauri is therefore balanced on the very precipice of what can be considered a true star. Its diameter is also incredibly small, measuring only about 1/7 of the Sun's, or approximately 211,000 kilometers. To put this into proper context for you, let's compare it to Jupiter, the gas giant in our solar system, which has a diameter of about 140,000 kilometers. This comparison reveals that our nearest star is only 1.35 times larger than Jupiter in diameter. If we could magically place Proxima Centauri where our Sun is, it would appear in the sky as a tiny, dim, cherry-red disk, a far cry from the brilliant star we know. These two fundamental properties, its low mass and low temperature, are precisely what make it invisible to us. Let's go back to the analogy of a campfire. A campfire's brightness is determined by two factors: the quantity of wood, which represents mass, and the intensity of the flames, which corresponds to temperature. Proxima Centauri has very little wood, and it burns at a very low temperature. Consequently, its luminosity, the total amount of energy it radiates each second, is practically insignificant when compared to the Sun. It amounts to only 17% of the Sun's output. If you were to imagine our Sun as a powerful 100,000-watt searchlight, Proxima Centauri would be equivalent to a tiny 17-watt LED. This staggering difference in luminosity is what fundamentally shapes how we perceive these two stars from our viewpoint on Earth. Astronomers use the stellar magnitude scale, which I have mentioned before, to measure the brightness of objects in space. This scale is logarithmic and works in a somewhat counterintuitive way. The larger the number, the fainter the object. Under ideal conditions, the limit of what the human eye can see is roughly the 6th magnitude, meaning anything with a magnitude of 7, 8, 9, or higher is imperceptible to us. Proxima Centauri's apparent magnitude is 11.13. This value makes it hundreds of times fainter than the threshold of human vision. Even if you were positioned in the darkest location on Earth, on a perfectly clear and moonless night, and you knew exactly where to aim your gaze, you would see absolutely nothing but an empty patch of the cosmos. To actually observe our nearest stellar neighbor, you require a telescope, and not just any basic model. Binoculars are unlikely to be sufficient. You would need an instrument with an objective lens measuring at least 8 centimeters in diameter to even begin to spot it. And even with such equipment, Proxima would appear as nothing more than an indistinct, faint, reddish point of light. Now, let's try to imagine we are not on Earth, but on a hypothetical planet orbiting either Alpha Centauri A or B. From that much closer distance, Proxima Centauri would present as a star of about the 5th magnitude. This means it would be visible to the naked eye, but it would be exceptionally faint, hovering right at the edge of visual perception. It would appear as just one among thousands of other similarly dim stars, offering no hint that it is a member of the very same star system. Entire civilizations could rise and fall beneath the light of 2 suns, completely unaware that their system contains a third, distant, and nearly invisible companion. And this leads us to the most crucial point I want to make. Red dwarfs, like Proxima, are not some kind of cosmic rarity. They are, in fact, the standard. Our galaxy, the Milky Way, is estimated to contain between 200 and 400 billion stars, and approximately 3/4 of them are these dim, cool, and small red dwarfs. When you gaze up at the night sky, what you are seeing is only the thinnest layer of cream, the rarest, most massive, and most brilliant stars that are visible across immense distances. It's akin to trying to understand the entire population of a major city by observing only its most famous celebrities and media figures. The vast majority of the galaxy's stellar inhabitants, these billions of red dwarfs, remain completely unseen by us. There are so many of them that, despite their insignificant individual masses, their collective mass constitutes a significant portion of the total stellar mass in the galaxy, around 30%. They are the quiet, invisible, yet foundational population of the stellar universe, and Proxima Centauri gives us the chance to study this most common type of star in exquisite detail, all because it happens to be right next door. We have now addressed the most straightforward layer of our query. The reason you cannot see Proxima Centauri is that it's a red dwarf, a star that is simply too small, too cool, and therefore too faint. While this is a basic physical explanation, it opens the door to a far more profound question. Why is it like this? What specific processes are unfolding within its core that make it so fundamentally different from its stellar siblings and our own sun? To find the answer, you and I must venture into the very heart of the star to grasp the physical laws that dictate its existence. A journey into a realm of immense pressures, staggering temperatures, and the universe's most essential process, nuclear fusion. So it's clear that Proxima Centauri is a red dwarf, a tiny, cool star whose faintness keeps it hidden from our view. But science is never content with simple observations. It always drives us to ask why. Why does Proxima Centauri differ so drastically from its neighbor, the sun-like Alpha Centauri A? Both stars originated from the same vast cloud of gas and dust approximately 4.85 billion years ago, meaning they share the same age and composition. The element that determines their profoundly different destinies comes down to a single, fundamental property: their mass. Mass is the beginning and the end of a star's story, dictating its size, temperature, color, luminosity, and even the length and manner of its life and death. To see how mass exerts such total control, you have to peer into the star's core, the location of the thermonuclear reactor that serves as its power source. Let's first deconstruct this process by looking at our sun, which we can then use as a baseline to understand the conditions within a red dwarf. Imagine the solar core, a region of truly incomprehensible extremes. The temperature soars to 15 million Kelvin. The pressure is 265 billion times that of the atmosphere at Earth's surface, and matter is compressed to a density 150 times greater than water. In this environment, matter exists as a plasma, a turbulent mixture of atomic nuclei and unattached electrons, predominantly composed of hydrogen nuclei, which are just single protons. Here, the immense gravitational force generated by the Sun's mass constantly tries to crush the core into an infinitely dense point. However, this inward pull is perfectly counteracted by the tremendous outward pressure from the thermonuclear reactions within. This delicate standoff, known as hydrostatic equilibrium, is what allows the star to remain stable for billions of years, with gravity pulling in and the core's energy pushing out. So, what exactly are these reactions that unleash such vast amounts of energy? The mechanism at play is known as the proton-proton chain reaction. In simplified terms, the process involves 4 hydrogen nuclei, that is, 4 individual protons, fusing together through a series of steps to create a single nucleus of helium. The fascinating part is that the mass of one helium nucleus is fractionally less than the total mass of the 4 protons that formed it. This missing mass doesn't just vanish, it is converted directly into pure energy, as described by Albert Einstein's celebrated equation E equals mc squared. While the mass lost in any single reaction is minuscule, the Sun's core converts around 600 million tons of hydrogen into helium every single second, releasing an amount of energy comparable to trillions of hydrogen bombs detonating simultaneously. This outpouring of energy, primarily in the form of gamma rays and neutrinos, is precisely what fuels the Sun's brilliance. Now, let's circle back to Proxima Centauri to see how this entire picture changes. With a mass that is only 12% of our Sun's, the crucial difference is the strength of its gravitational compression. Because Proxima's mass is so much lower, its gravitational pull is substantially weaker, preventing it from squeezing its core with the same intensity as the Sun. Consequently, the pressure in its core is far less, which in turn leads to a much lower temperature. It is estimated that Proxima Centauri's core is only around 4 million Kelvin, nearly 4 times cooler than the core of our Sun, a factor that proves to be absolutely decisive.
The rate at which thermonuclear reactions occur is incredibly sensitive to temperature. As you'll recall, protons carry a positive charge and therefore naturally repel one another. For them to merge, they must overcome this powerful electrostatic barrier. Although a quantum mechanical phenomenon called tunneling assists in this process, the fundamental rule remains. The higher the temperature, the more rapidly the protons move, the more frequently they collide, and the greater the probability that they will successfully fuse together. Let me offer you an analogy. Picture a vast, dark room, filled with people moving about at random. And our goal is for them to find each other and shake hands. The efficiency of this process depends on both the density of people in the room and their speed. The Sun's core is like an incredibly crowded room where people are dashing around at immense velocities, causing collisions to happen constantly. In contrast, Proxima Centauri's core is also a crowded space, but its occupants are moving at a much slower, almost leisurely pace, which means that the collisions leading to a handshake, representing nuclear fusion, occur far, far less frequently.
Just how much less frequently? The energy output of a star's core is proportional to its temperature raised to approximately the 4th power. This relationship means that even a modest reduction in temperature results in a dramatic decline in energy generation. Since the temperature in Proxima's core is almost 4 times lower than the Sun's, its rate of nuclear fusion is not merely 4 times less, but hundreds of times less. You could think of it like this. The Sun is a powerful, high-octane racing engine running at full throttle, consuming immense quantities of fuel to produce enormous power. Whereas Proxima Centauri is more like the tiny, efficient engine of a lawnmower. It functions at the most minimal revolutions, sipping fuel with incredible efficiency, which naturally results in a very low power output. This incredibly slow, measured rate of nuclear fusion serves as the fundamental explanation for why red dwarfs are so faint. They generate energy at a pace that is thousands of times slower than stars similar to our Sun. Once this energy is created in the core, it must embark on a lengthy voyage to the star's surface. This brings us to the second crucial distinction between Proxima and the Sun: the way they transport energy. Inside the Sun's core, energy is produced as high-energy gamma quanta. These photons are unable to travel directly outward, as they are perpetually absorbed and re-emitted by plasma particles, executing a random walk through the radiative zone. The journey of a single photon from the core to the Sun's surface can stretch over hundreds of thousands of years. Energy transport in the Sun changes only in its outer third, where the plasma grows dense enough to necessitate a different method: convection. This process is much like water boiling in a kettle, where immense bubbles of hot plasma ascend, release their heat, cool off, and then descend back into the interior. Within a red dwarf, such as Proxima Centauri, the situation is entirely different. Its low mass and cooler temperatures render its interior far more opaque to radiation, making radiative transport almost completely ineffective. Instead, the entire star, from its very heart to its outer atmosphere, is gripped by convection. You have to imagine all the material inside Proxima Centauri being in a state of constant, thorough churning, like a pot of soup that is ceaselessly stirred. Hot matter from the core, now enriched with the helium byproducts of fusion, rises toward the surface. In turn, cooler material from the surface, still rich with fresh hydrogen fuel, sinks directly into the core to be consumed in the nuclear furnace. This profound structural difference leads to two incredible consequences. The first is its direct influence on the star's magnetic activity, which, as you will discover later, is its most significant and hazardous secret. The second, which is almost beyond our ability to grasp, is that this process makes red dwarfs virtually immortal on any human timescale. In a star like the Sun, nuclear fusion is confined strictly to the core, meaning the hydrogen in its outer layers will never reach the reaction zone. Consequently, the Sun can only ever use about 10% of its total hydrogen reserves. The moment the hydrogen in its core is depleted, the Sun will begin its death throes, expanding into a red giant. Proxima Centauri, however, thanks to its complete convective mixing, can consume nearly all of its hydrogen fuel, utilizing its entire fuel tank with 100% efficiency. When you combine this total fuel utilization with its exceptionally slow consumption rate, what is the result? You get a lifespan of staggering length. The estimated time our Sun will spend on the main sequence is around 10 billion years. Having already lived for about 4.6 billion years, it is roughly at the midpoint of its active existence. By contrast, a red dwarf like Proxima Centauri has a projected lifetime of several trillion years. Trillions of years. That is a duration hundreds of times longer than the current age of the universe, which stands at approximately 13.8 billion years. Consider what this means. Proxima Centauri, that dim and unseen speck in our night sky, is a sentinel of the deep future. It will continue to glow, much as it does today, long after our Sun has dwindled into a cold white dwarf. It will still be shining when the Andromeda galaxy merges with our own Milky Way, and it will persist even after the last of the universe's massive stars have long since exploded and faded from view. The era when the cosmos is filled with brilliant stars is merely a fleeting moment near its inception. The universe's long-term future belongs to these faint, economical, and enduring red dwarfs like Proxima. Its quiet, almost imperceptible glow is the light of eternity, and grasping this fact transforms our perspective. We cease to view it as just a feeble star and begin to recognize it as a time machine, offering a glimpse into an epoch humanity will never see. And all of this emerges as a direct outcome of the physical laws governing its tiny, slowly beating heart. In the last segment, we journeyed into the core of Proxima Centauri and found that its faintness is a direct product of its low mass. The combination of sluggish nuclear reactions and complete convective mixing makes it extraordinarily frugal with its fuel. However, these very same processes give rise to a consequence that is nearly impossible for us to fully comprehend. They bestow upon red dwarfs a lifespan that is practically eternal. Let's delve into this concept further, as it truly upends our intuitive understanding of stars and time. When I refer to a star's lifespan, I am typically talking about its active phase of existence, the period known as its time on the main sequence. This is the stage during which a star consistently fuses hydrogen into helium within its core, a phase that our Sun and the vast majority of stars you see in the sky currently occupy. The length of this phase is governed by two key factors: the total amount of fuel available and the speed at which that fuel is consumed. Let's go back to our automobile analogy to illustrate this. Picture two different cars. The first is a high-performance sports car with a massive engine. This represents our Sun. It has a large fuel tank, perhaps 100 liters, but its powerful engine burns through fuel at a ferocious rate, using 20 liters for every 100 kilometers it travels. Our second car is a small, economical city car, which stands in for Proxima Centauri. Its fuel tank is substantially smaller, holding only 12 liters, which corresponds to its mass being 12% of the Sun's. Yet, its tiny engine is so remarkably efficient that it requires only 1 liter of fuel to cover 100 kilometers. Now, if we calculate which of these cars can travel a greater distance, the results are striking. The Sun, our powerful sports car, will run out of fuel after just 500 kilometers. In contrast, Proxima, the compact car, will travel a full 12,000 kilometers despite its minuscule tank. The disparity is immense, but even this comparison is incomplete as it fails to include the most vital mechanism of all, the mixing of the fuel. Let's refine that idea. Picture the fuel pump in the Sun's metaphorical sports car, which can only access gasoline from the very bottom of its tank, using a mere 10% of the total volume. With the remaining 90 liters inaccessible, its actual driving range plummets to just 50 kilometers. In stark contrast, Proxima's compact car features a brilliant system that continuously mixes all the fuel in its tank. This represents complete convection. This efficiency allows the car to utilize every last drop of its 12 liters, giving it a range that remains at 12,000 kilometers. When you now compare these outcomes, 50 kilometers for the high-powered sports car versus 12,000 for the humble compact, the disparity becomes truly astronomical. This analogy perfectly illustrates what occurs with stars. Over its entire lifespan, the Sun will only consume about 10% of the hydrogen located in its core. Once this primary fuel is depleted in approximately 5 billion years, its core will contract and grow hotter, causing the outer layers to swell dramatically as the Sun transforms into a red giant. During its red giant phase, the Sun's size will expand so immensely that it will engulf Mercury, Venus, and perhaps even our own planet, Earth. Following this turbulent but relatively short period, it will cast off its outer layers, creating a magnificent planetary nebula. What is left behind will be a tiny, extraordinarily dense object known as a white dwarf, which is destined to cool slowly over trillions of years, marking the typical fate for stars of its kind. So, what does the future hold for Proxima Centauri? Its destiny is set to be far less spectacular but profoundly longer. Because of its complete convective mixing, it will meticulously and gradually burn through nearly all of its hydrogen supply, converting it into helium. This process is expected to last for an almost incomprehensible duration, with current estimates placing Proxima Centauri's main sequence lifetime somewhere between 2 and 5 trillion years. To really appreciate that number, consider that a trillion is 1,000 billion. Our entire universe is currently only 13.8 billion years old, which means Proxima Centauri is set to live hundreds of times longer than the cosmos has existed thus far. The whole history of space and time, from the Big Bang until today, represents nothing more than a brief introductory paragraph in the epic biography of this small star. When Proxima Centauri finally depletes the majority of its hydrogen, it will not expand into a red giant. Its mass is simply insufficient to initiate helium fusion within its core. Instead, it will gradually contract and heat up, becoming hotter and more luminous as the concentration of helium inside it increases. At the pinnacle of its evolution, trillions of years from now, it will morph into what scientists theorize as a blue dwarf, a hypothetical class of star that is yet to exist anywhere in the universe. After its time as a blue dwarf, once the last of its hydrogen fuel is finally gone, Proxima Centauri will smoothly and without any violent outbursts collapse into a white dwarf, composed primarily of helium. From that point on, much like the remnant of our Sun, it will spend an eternity slowly cooling in the vast, dark emptiness of the future universe, ultimately becoming a cold, non-luminous body known as a black dwarf. This perspective on deep time compels you to view the cosmos in an entirely new light. We are accustomed to perceiving the universe as a theater of swift and violent events. Supernova explosions, collisions between galaxies, and the dramatic birth and death of stars. This is certainly accurate for massive stars, whose lives are brilliant but fleeting as they rapidly burn their fuel and die, enriching the cosmos with the heavy elements needed to form new stars and planets like our own. However, red dwarfs are the true keepers of cosmic time, as they are playing a much longer game. A period will eventually arrive, which astrophysicists refer to as the era of stellar degeneracy. Roughly 100 trillion years after the Big Bang, the active formation of new stars in galaxies will halt, because the necessary gas will be exhausted. By then, all massive stars will have long since burned out, leaving red dwarfs as the only sources of light in the cold, ever-expanding universe. I want you to envision this future scene. Galaxies, having lost their bright spiral arms, will appear as dark clusters of faint red points of light and cooling white dwarfs. From the surface of any planet, the night sky will look utterly different, not a brilliant tapestry of diamonds, but a barely perceptible red glow cast by these seemingly eternal stars. This is precisely why the study of Proxima Centauri holds such immense significance for us today. Proxima is more than just our closest stellar neighbor. It offers a glimpse into the universe's distant future. By observing it now, we are delving into the physics of the very objects that will come to dominate the cosmos on timescales that defy human imagination. This realization also carries profound implications for the search for extraterrestrial life. On one hand, the incredible longevity of red dwarfs provides any hypothetical life on their planets a vast stretch of time to emerge and evolve. If complex life managed to develop on Earth in 4 billion years, you can only imagine what evolutionary processes could accomplish over 100 billion, or even 1 trillion years. opening the door to the most ambitious speculations. On the other hand, as we are about to explore, this situation has a distinct downside. Young red dwarfs, such as Proxima, can be exceptionally active and unstable, rendering their planetary systems profoundly inhospitable for life to take hold. Perhaps life can only arise around very old, tranquil red dwarfs, which are currently beyond our ability to observe. In this way, Proxima Centauri imparts a lesson in cosmic humility. With our brief lifespans on a planet circling a star with a finite reserve of fuel, we represent merely a fleeting moment in the grand scheme of things. The real marathon runners, the genuine survivors of the universe, are these modest, unseen red dots scattered across the cosmos.
Their dim light is not an indication of weakness, but rather a testament to their incredible efficiency and endurance. These stars have adopted a different strategy entirely. Not to burn with intense brightness, but to shine for an extraordinary length of time. And when it comes to that strategy, you will find that they are the absolute champions. Grasping this single concept is the very key to unlocking the puzzle of Proxima's invisibility, and it also holds profound implications for understanding the basic structure and ultimate destiny of our universe. The reason you don't see it is that our perception and awareness are calibrated for things that are brilliant and ephemeral. Proxima Centauri represents the quiet, enduring murmur of the cosmos, which you can only discern by listening with intense focus. Up to this point, I have described Proxima Centauri as a faint, feeble, and nearly imperceptible star. And from the standpoint of human sight, that is entirely accurate. Your eyes, molded by millions of years of evolution beneath a yellow sun, are incredibly sophisticated yet narrowly focused instruments. They are masters at detecting the small sliver of the electromagnetic spectrum that we refer to as visible light. However, this visible light is merely a tiny crack in the immense window through which the universe reveals itself to us. Beyond this limited range, from violet to red, exist whole domains of radiation that your eyes are incapable of registering, such as radio waves, microwaves, ultraviolet, and X-rays. Crucially for our story, this also includes infrared radiation, and it is within this unseen realm that another piece of the puzzle lies, answering why Proxima Centauri appears so faint to you. The problem isn't just that the star generates a small amount of energy, but rather the specific form that energy takes when it radiates outward. Let's delve back into physics for a moment. Any object with a temperature above absolute zero emits electromagnetic waves in a process known as thermal radiation. The character of this radiation, specifically the wavelength where its intensity is greatest, is directly tied to the object's temperature, a relationship described by a fundamental principle called Wien's displacement law, which states that the hotter something is, the shorter its peak emission wavelength becomes. Picture a piece of metal as we begin applying heat to it. Initially, it is just warm and shows no visible glow. But if you were to look at it with a thermal imager that detects infrared, you would see it shining brightly. As the metal gets hotter, it starts to glow a deep red, then shifts to a vibrant orange, then yellow, until at extreme temperatures it blazes with a brilliant white or even a bluish hue. What you are witnessing is the peak of its energy emission, moving from the infrared band into the visible spectrum and beyond, toward progressively shorter wavelengths. Now, let's extend this principle to the stars. Our Sun maintains a surface temperature of approximately 5,800 Kelvin. At this heat, its emission peak lands right in the center of the visible spectrum, within the green wavelength range. Your eyes have evolved to be most sensitive to this light, which is why you perceive the Sun as white,
as it radiates with great efficiency in the spectrum you can see. In contrast, let's examine Proxima Centauri, whose surface temperature, as we've established, is only around 3000 Kelvin. In accordance with Wien's displacement law, its peak emission doesn't occur in the visible spectrum at all. Instead, it falls within the near-infrared range at a wavelength of about 960 nanometers, while the human eye's perception cuts off around 700 nanometers. This means the vast majority of photons streaming from Proxima Centauri fly past you without ever registering on your retinas. You are only able to perceive the very faint edge of its energy distribution that spills over into the red portion of the visible spectrum.
Let's try a sonic analogy to clarify this. Imagine two vocalists. The first, like our sun, sings in a comfortable mid-range that your ears capture perfectly, making his voice sound robust and clear. The second singer, representing Proxima Centauri, performs in an extremely low infrasonic register, at frequencies your ears are physically unable to process. You might only catch the highest harmonics of his voice that just barely creep into your audible range, making it seem like he is singing in a near whisper. In truth, if you had specialized microphones attuned to infrasound, you would discover his voice is immensely powerful. It just operates on a different frequency. This is precisely the situation with Proxima Centauri. To your unaided eyes, it is a dim, almost unnoticeable speck of light. Yet, if you had the ability to see in the infrared spectrum, the entire picture would be radically transformed. In near-infrared light, Proxima Centauri is one of the most luminous stars in the heavens, far outshining many of the titans that dominate our view in visible light. You don't see it because it isn't shining, but because your biological sensors are simply tuned to a different wavelength. This understanding completely reshaped the field of astronomy. During the 20th century, scientists came to grips with the fact that by confining their observations to visible light, they were discarding a vast amount of cosmic information. This marked the beginning of multi-wavelength astronomy, leading to the creation of telescopes designed to see in radio, infrared, ultraviolet, X-ray, and gamma-ray frequencies, which utterly altered our vision of the cosmos. For the study of cooler objects, such as red dwarfs, brown dwarfs, and the molecular clouds that serve as stellar nurseries, infrared telescopes have been indispensable. However, observatories on the ground encounter a significant hurdle. Earth's atmosphere, particularly its water vapor, heavily absorbs infrared radiation. This is why the premier infrared observatories are constructed at high altitudes in arid regions, like the facilities in Hawaii or Chile's Atacama Desert. But the truly monumental advance occurred when we gained the ability to position infrared telescopes in space, free from the distorting effects of our atmosphere. Spacecraft such as Spitzer and Herschel, and now the most magnificent of them all, the James Webb Space Telescope, have unveiled the universe in its genuine, unseen glory. To these instruments, Proxima Centauri is no dim outcast, but a brilliant and perfect subject for investigation. With its massive mirror and unmatched sensitivity to infrared light, James Webb can examine Proxima Centauri and its system of planets with extraordinary detail, even analyzing its light spectrum to ascertain the chemical makeup of its atmosphere. The James Webb Telescope can try to directly capture the light reflected by its planets, or even register the heat radiating from their surfaces. What seems to us like near-total blackness is, for this observatory, a brightly lit stage where a cosmic play is constantly in motion. This difference in perception carries a deep philosophical weight, teaching us that the human view of the universe is not absolute, but merely one of many possible outlooks.
To a bee, the world unfolds in ultraviolet light, revealing patterns on flowers that guide it to nectar, making them look entirely different. A snake perceives the thermal signature of its prey in the dark. In the same way that we must learn to view the cosmos through instruments tuned to different wavelengths, we are also required to broaden our entire framework of understanding. With this knowledge, we can offer a more thorough and nuanced answer to the question of why you can't see Proxima Centauri. First, its low mass and slow rate of nuclear fusion mean it generates substantially less energy than the Sun. Second, the energy it does release is predominantly in the infrared portion of the spectrum, which is entirely invisible to the human eye. And this combination of factors keeps our closest stellar neighbor a phantom in the night sky.
This entire narrative is not about an absence of light, but rather about a form of light that we are not biologically equipped to perceive. It serves as a potent reminder that reality is invariably richer and more intricate than the picture our senses can provide. To genuinely comprehend our neighbor, we had to move beyond our biological constraints and invent new eyes, instruments capable of seeing in infrared light, which transformed Proxima Centauri from an unseen speck into a brilliant beacon. However, as we are about to discover, this beacon shines with a volatile, ferocious, and potentially lethal radiance. While we may have solved the puzzle of its invisibility, its primary and most disconcerting secret still lies ahead. We have journeyed a great distance to grasp why Proxima Centauri remains hidden, learning that it is a small, cool red dwarf, a star that husbands its energy and is destined to live for trillions of years. Knowing that most of its light is emitted in the infrared range, invisible to our eyes, completes this initial picture. All these details contributed to an image of a serene, stable, and almost drowsy star, a humble and unassuming neighbor living a quiet life on the edge of a solar system. For many decades, this was precisely how astronomers saw red dwarfs, as perfect candidates for nurturing habitable worlds, since their immense lifespans would offer life a virtually infinite amount of time to emerge and evolve. Knowing that most of its light is emitted in the infrared range, invisible to our eyes, completes this initial picture. All these details contributed to an image of a serene, stable, and almost drowsy star, a humble and unassuming neighbor living a quiet life on the edge of a solar system. For many decades, this was precisely how astronomers saw red dwarfs, as perfect candidates for nurturing habitable worlds, since their immense lifespans would offer life a virtually infinite amount of time to emerge and evolve. But the more intently we studied these placid neighbors, the more apparent it became that a turbulent and erratic nature was concealed behind this tranquil exterior. Proxima Centauri proved to be the most dramatic and immediate illustration of this duality, which brings us to its greatest secret. It is not merely a red dwarf, it is a flare star, whose eruptions are so furiously powerful they could render any world in its vicinity a sterilized wasteland. A stellar flare is, in principle, a phenomenon quite similar to the solar flares we observe on our own sun, but on Proxima Centauri they occur on a completely different and catastrophic level. To grasp their origin, we must revisit the star's internal composition, specifically its magnetic field. A star's magnetic field is produced through a mechanism known as the stellar dynamo, which relies on two essential components: the churning of electrically conductive plasma, called convection, and rotation. Our Sun possesses both of these ingredients, but as you may recall, convection in the Sun is confined to its outer third. The deeper radiative zone rotates at a different speed from the outer convective layers, and this discrepancy, known as differential rotation, stretches and twists magnetic field lines as if they were elastic bands.
Occasionally, these bands become so tangled that they break through the surface, creating sunspots. And when the tension builds to an extreme, they abruptly snap and reconnect. This event, referred to as magnetic reconnection, unleashes a colossal amount of stored energy as a flare, a powerful burst of charged particles and intense radiation spanning the entire electromagnetic spectrum, from radio waves to X-rays. Now, if we turn our attention back to Proxima Centauri, we find a different situation. First, as we know, it is fully convective, meaning its entire volume from the core to the surface is in a constant state of roiling and mixing, which generates far more chaotic and complex plasma dynamics than in our Sun. Second, Proxima Centauri spins on its axis rather slowly, completing one turn in about 83 Earth days, whereas the Sun's equator rotates once every 25 days. You might assume that a slower rotation would lead to a weaker dynamo effect, but this is where the intricate interplay between deep convection and rotation becomes crucial. It appears that even a slow spin, when combined with such violent convection, can generate magnetic fields that are incredibly strong and convoluted, on average, much more powerful than the Sun's. The surface of Proxima Centauri is therefore blanketed in gigantic star spots, which are regions of exceptionally intense magnetic fields that can take up as much as 20% of its total surface area. To put that in perspective, sunspots cover less than 1% of the Sun's surface, even during its most active periods. These immense magnetic formations are in a constant state of flux, as turbulent plasma flows stretch and twist their field lines. When these lines reach their breaking point, a flare is triggered, but the magnitude of these events is simply not comparable to what we witness on the Sun. A solar flare might augment the Sun's total brightness by a tiny fraction of a percent for a very brief period, which is nearly unnoticeable to us on Earth, though it can trigger auroras and disrupt satellites. In contrast, a flare on Proxima Centauri can increase its visible luminosity by 10, 100, or even 1,000 times over. Picture a star, normally so faint you can hardly see it with a telescope, abruptly flaring into a prominent point of light for a matter of minutes or hours. The earliest clues to Proxima's volatile behavior surfaced in the mid-20th century, as scientists observed its erratic fluctuations in luminosity. However, the true magnitude of this activity wasn't fully grasped until the arrival of advanced tools that allowed for uninterrupted observation of the star. What these continuous observations revealed was simply astounding. Proxima Centauri erupts with several potent flares on a daily basis, and occasionally it unleashes what are known as superflares. In 2016, a team using the ALMA telescope in Chile happened to capture one such event, witnessing the star's brightness in the millimeter radio spectrum increase by a factor of 1,000 in a mere 10 seconds. This particular outburst was 10 times more intense than any comparable solar flare ever documented on our own Sun. Yet, that display was far from the star's ultimate capacity. The most extreme outburst was documented on May 1, 2019, by an astronomy team under the direction of Meredith McGregor from the University of Colorado Boulder. Through the coordinated use of 9 telescopes at once, including the Hubble Space Telescope, they had the extraordinary fortune to observe the most powerful flare ever seen, not only from Proxima, but from any star of its class. Over a span of just 7 seconds, the star's ultraviolet luminosity skyrocketed by a factor of 14,000. And no, that number isn't a mistake. For a brief period, this ordinarily dim and diminutive star transformed into one of the most brilliant ultraviolet emitters in the entire night sky. The sheer energy unleashed by this single event was 100 times greater than that of any solar flare ever measured from the Sun. To help you comprehend this immense scale, let's use another comparison. Think of Proxima Centauri as a quiet individual sitting humbly in the corner of a room, who then, without any warning, erupts with a shriek that surpasses the sound of a jet engine at takeoff. This stark difference between its normal, placid state and the violence of its flares fundamentally alters how we see it. It's not merely a peaceful neighbor anymore. It's a neighbor prone to devastating and unpredictable outbursts of fury.
This rage has immediate and disastrous implications for anything in its vicinity, most notably its planets. During a superflare, the star releases far more than just an intense blast of electromagnetic radiation, including ultraviolet and X-rays. These eruptions are frequently coupled with a coronal mass ejection, a massive cloud of plasma composed of protons and electrons hurtling through space at incredible velocities. Any planet in a close orbit is therefore subjected to a devastating 1-2 punch. Initially, the world is saturated with a wave of Hard radiation, intense enough to sterilize its surface and shatter complex organic molecules. Hours later, the plasma cloud slams into its atmosphere with the force of a colossal hammer. Over millions of years, this process, known as atmospheric erosion, can completely scour away a planet's gaseous shell, leaving only a barren, lifeless rock in its wake. This violent, erratic character is Proxima Centauri's greatest secret, long concealed by its seemingly faint and ordinary appearance. We sought a calm port near our solar system's closest stellar neighbor, but what we discovered was a furious tempest. This dual nature, defined by periods of calm punctuated by violent eruptions, is a defining characteristic of many red dwarf stars, particularly those that are young and spin rapidly. Their deep convection, which produces intense magnetic fields, is responsible for both their incredibly long lifespans and the hazard they pose to their own planetary systems. For many astrobiologists, grasping this reality was a sobering moment, as the prospect of discovering a habitable planet around the galaxy's most numerous type of star ran headlong into the unforgiving principles of stellar physics. This stark truth took on a particularly dramatic dimension in 2016, when scientists revealed the existence of a planet orbiting directly within this celestial firing range. This planet, circling Proxima Centauri, meets all the formal requirements to be situated in what is called the habitable zone, transforming an abstract problem into the tragic narrative of a world perilously close to a fiery dragon. The Alpha Centauri system has fascinated humanity for centuries, capturing our collective imagination. As our closest stellar neighbors, with two of its stars resembling our own sun, it appeared to be the ideal location to begin the search for alien worlds. Science fiction visionaries and authors have long dispatched their fictional starships to this system, imagining its hypothetical planets teeming with advanced societies. For the scientific community, however, this remained a distant dream for a very long time. The hunt for planets orbiting other stars, known as exoplanets, presents an enormous technical challenge. You can compare it to attempting to see a firefly on the edge of a powerful searchlight from hundreds of kilometers away. Exoplanets produce no light of their own, merely reflecting the illumination from their parent star, a reflection that is billions of times dimmer and is completely lost in the star's overwhelming glare. Consequently, viewing an exoplanet directly is nearly impossible, a feat achievable only by our most powerful telescopes, and then only under exceptionally rare circumstances. Scientists were compelled to devise clever workarounds, creating indirect techniques to identify a planet based on the subtle effects it has on its host star. Among the most effective of these techniques is the radial velocity method, also referred to as Doppler spectroscopy. The underlying concept is remarkable for its straightforwardness. As a planet circles a star, it isn't the only object in motion.
Its gravitational pull also tugs on the star itself. This causes the star to execute minute wobbles around their shared center of mass, the barycenter, rather than remaining perfectly still. You can visualize this like an athlete swinging a heavy hammer who must also shift their own body slightly to stay balanced. While we cannot possibly see these tiny stellar movements directly, we possess the technology to measure their consequences. When the star executes its subtle orbital dance and moves toward us here on Earth, the Doppler effect causes the wavelength of its light to compress slightly, shifting it toward the blue portion of the spectrum. Conversely, as the star recedes, its light stretches toward the red end. These recurring shifts in the star's spectral lines, a barely detectable stellar pulse, reveal the existence of an unseen companion. The velocity of these movements, known as the radial velocity, is astonishingly small. For a planet the size of Jupiter, it measures in the tens of meters per second, while for an Earth-sized world, it is merely a few centimeters per second, equivalent to the pace of a crawling snail. Imagine the immense difficulty of this task. To measure the velocity of a star some 40 trillion kilometers away, with the precision needed to detect a person's walking speed. It was precisely to overcome this challenge that the world's most precise spectrographs were developed. One premier example of such an instrument, a true planet-hunting machine, is HARPS, which stands for the High Accuracy Radial Velocity Planet Searcher. This device is mounted on the 3.6-meter telescope at the Lucia Observatory in Chile, which is managed by the European Southern Observatory. HARPS is an engineering masterpiece, able to measure the radial velocities of stars with an accuracy of 1 meter per second. And it was this very instrument that became central to a project destined to make history. In 2013, a group of astronomers under the leadership of Guillaume Anglada-Escudé from Queen Mary University of London initiated an observation campaign they called Pale Red Dot. The name is a clever homage to the renowned Pale Blue Dot image of Earth captured by Voyager 1, but its focus was on finding a planet orbiting our nearest stellar neighbor, a red dwarf. The project's aim was the systematic, long-term observation of Proxima Centauri with the HARPS spectrograph. Night after night, the scientists diligently gathered data, building a comprehensive record of the star's radial velocity. This work demanded extraordinary patience and precision. As we now understand, Proxima Centauri is an exceptionally active star. Its powerful flares and the turbulent motion of convective plasma on its surface introduce noise into the data that can easily be mistaken for a planetary signal. The researchers had to meticulously separate the genuine signal from this background chaos. After analyzing several years of accumulated data, they successfully isolated a faint but consistent periodic signature. Proxima Centauri's radial velocity was fluctuating with an amplitude of just 1.4 meters per second, the speed of a person walking at a leisurely pace, and these fluctuations repeated with a distinct period of 11.2 Earth days. An oscillation like this could only be attributed to one thing: a planet in orbit around the star. On August 24, 2016, an article appeared in the journal Nature that sent shockwaves through the scientific community and beyond. The Pale Red Dot team formally announced their discovery of a planet orbiting the star closest to our Sun, which was subsequently named Proxima Centauri b, or Proxima b for short. This was not merely another entry in the growing catalogue of exoplanets. It was something profoundly significant. For the first time, humanity had found our closest extrasolar neighbor, a world located just 4.2 light-years away. Up until that point, the nearest confirmed exoplanet was situated more than 12 light-years from us. This discovery fundamentally changed our perspective. For the first time in history, you could gaze up at the nearest star in the night sky, knowing that a planet accompanies that faint point of light. The vast emptiness of space suddenly felt less abstract and more tangible, now containing a concrete, albeit distant, destination for future generations. The data from the radial velocity signal allowed scientists to determine the planet's minimum mass, which came out to approximately 1.17 Earth masses. This places Proxima b firmly in the category of terrestrial planets, meaning it is most likely a rocky world similar to Earth, Venus, or Mars.
Its orbital period of 11.2 days indicates that it circles its star at an incredibly close distance of only 7.5 million kilometers. This is roughly 1/12 of the distance from the Earth to the Sun, and is significantly closer than even Mercury's orbit. Under normal circumstances, such proximity would suggest a hellish, molten landscape. However, it is crucial to remember that Proxima Centauri is a dim red dwarf, emitting thousands of times less energy than our Sun. This is where the story takes a fascinating turn. There is a concept in astrobiology known as the habitable zone, often called the Goldilocks zone, which describes the orbital region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface.
Since red dwarfs are so faint, their habitable zones are located very near to them. Amazingly, calculations revealed that Proxima b, despite its tight orbit, is situated directly within this life-friendly region. The planet receives about 65% of the energy flux that Earth gets from the Sun, which is sufficient to support moderate surface temperatures, assuming it possesses a suitable atmosphere. This news sparked imaginations worldwide. An Earth-sized planet orbiting the nearest star and located in the habitable zone. The hope of discovering a second Earth, another cradle for life, suddenly felt tantalizingly close to becoming a reality. Headlines across the globe shouted about a second habitable Earth, and fervent discussions erupted about what this new world might be like. Scientists, however, remained much more cautious. They were keenly aware that residing in the habitable zone is merely a preliminary requirement for life, and is by no means a guarantee of habitability. In the case of Proxima b, every encouraging piece of data seemed to be countered by several deeply concerning factors. The most critical of these issues is tidal locking. Due to the immense gravitational pull from the star at such a short distance, the planet is almost certainly in a state of synchronous rotation.
This configuration means the planet is tidally locked, consistently presenting the same hemisphere to its star, much like our moon does with Earth.
Consequently, one side of the planet is trapped in eternal daylight and searing temperatures, while the opposite side endures perpetual night and bitter cold. The only area that might support life is a thin band along the day-night divide, the so-called terminator, where a constant twilight persists.
Yet, even the challenges of tidal locking seem minor when compared to the violent, unpredictable nature of the star itself, a threat we've already covered. The discovery of Proxima b positioned this theoretical world directly in the path of its star's fury. A planet orbiting this closely must endure the full force of its star's colossal flares, which bombard it daily with X-ray and ultraviolet radiation hundreds or even thousands of times more potent than what Earth gets from the Sun.
So what exactly is Proxima b?
Is it a potential haven or a wasteland scorched by radiation? Does it represent a new hope for humanity, or is it a cautionary tale of a world with a tragically hostile parent star? The finding of this planet generated far more questions than it provided answers, transforming Proxima Centauri from a distant point of light into the setting for a cosmic drama. To grasp the fate of this world, we had to look even more closely at this planetary protagonist, orbiting its fiery dragon.
The announcement of Proxima B's discovery ignited a wave of public excitement that was perhaps rivaled only by humanity's first steps on the moon. In the collective imagination, the image of a second Earth, a potential interstellar neighbor, rapidly took hold. The notion of an Earth-sized, rocky planet within the habitable zone of the nearest star was simply too compelling to dismiss. But in the world of science, initial excitement is always followed by sober and often unforgiving analysis. The more scientists modeled the environment on Proxima b, the more desolate the picture became, and the dream of a paradise world started to crumble against the harsh realities of astrophysics. It appears that residing in the Goldilocks zone of a red dwarf is akin to trying to warm yourself by a bonfire but standing so close that the flying sparks ignite your clothing. Let's systematically go through all the factors that likely convert this potentially habitable world into a sterile desert. The primary antagonist for any life on Proxima b is unquestionably the ferocious activity of its star. While we've mentioned the massive flares, let's now quantify their real impact. Even during its quiet periods, Proxima Centauri unleashes a stream of X-ray radiation that is approximately 400 times more powerful than the Sun's. This alone establishes an incredibly hostile radiation environment for the planet. During superflares, like the one observed in 2019, this already dangerous situation becomes truly catastrophic, as the flux of X-rays hitting the planet can surge by tens of thousands of times. Any organism on the surface not shielded by a deep layer of water or rock would be sterilized almost instantly. Furthermore, intense ultraviolet radiation, particularly in the UVC and UVB spectrums, destroys complex organic compounds, including DNA, making the surface of any ocean completely sterile and likely precluding the evolution of complex, land-based life.
However, this intense radiation is only one part of the problem. A second, and perhaps even more critical, danger is the planet's constant exposure to a barrage of charged particles, known as the stellar wind. Our Sun also produces a solar wind, but Earth is largely protected from it by our global magnetic field. This invisible shield deflects the majority of the particle stream, allowing only a small amount to enter near the poles, where it creates the beautiful and harmless auroras. We have no way of knowing if Proxima b possesses a similar magnetic field, but even if it did, it would be confronted with a challenge far greater than anything Earth's magnetosphere has ever faced. The stellar wind from Proxima Centauri is substantially denser and more energetic, and during the coronal mass ejections that accompany flares, the planet is struck by a veritable plasma tsunami, exerting pressure thousands of times greater than what the solar wind applies to Earth's magnetic field. Computer simulations from the Harvard-Smithsonian Center for Astrophysics have demonstrated that even a very powerful magnetic field would be insufficient to fully shield the planet. The immense force of the stellar wind would compress the magnetosphere so severely that it would expose the planet's poles, creating a direct pathway for charged particles to pour into the upper atmosphere. This is the point where a process known as atmospheric erosion, or sputtering, would begin. This process is like a cosmic game of billiards. Incoming charged particles collide with molecules of atmospheric gas, like nitrogen, oxygen, or carbon dioxide, transferring their energy and accelerating them. If a gas molecule gains enough speed, it can escape the planet's gravitational pull and be lost to space forever. While this occurs constantly, the rate of loss would accelerate by thousands of times during a flare. Over billions of years, this relentless bombardment could have stripped Proxima b of an atmosphere as dense as Earth's. Models suggest that even if the planet initially had a thick, gaseous envelope and vast oceans,
the stellar wind and flares could have effectively blown them into space. First, the lightest gases, like hydrogen, would have escaped, followed by oxygen and nitrogen, ultimately leaving behind a dry, airless rock similar to our own Mercury or the Moon. Now, let's briefly turn our attention from the star's flares to another significant issue, the aforementioned tidal locking.
Given its nearness to the star, the planet is almost certainly tidally locked, a condition that results in a climate of severe extremes. The day side, in a state of constant exposure to the star, could experience temperatures hot enough to boil water, even with the star's low luminosity. Conversely, the night side is trapped in perpetual darkness, with conditions likely mirroring Antarctica, where atmospheric gases could freeze solid and precipitate onto the surface like snow. Ideally, a thick atmosphere could circulate heat from the star-facing hemisphere to the dark one, moderating the temperature differences with powerful winds. However, as we've already discussed, sustaining a substantial atmosphere under these harsh conditions is next to impossible. This leads to the most probable scenario, a world of stark divisions with one side a blistering inferno and the other an icy desert. Caught between these two extremes, the thin Terminator zone, the twilight strip where temperatures might be livable, would be ravaged by constant hurricane-strength gales flowing from the scorching day side toward the frigid night. There is also a different, more subtle, yet equally critical factor to consider, the planet's formation. Proxima b orbits extremely close to its star, well within what astronomers call the snow line. This is a theoretical boundary in a young star's protoplanetary disk, beyond which compounds like water can freeze into ice. Planets that form inside this line tend to be born as dry, rocky bodies. It is believed that Earth acquired its water much later through a relentless bombardment of asteroids and comets originating from the colder, outer reaches of our solar system. We have no way of knowing if a similar series of events occurred in the Proxima Centauri system. It's quite plausible that Proxima b started as an arid world and never accumulated the significant water reserves necessary to create oceans, a scenario that would render the entire discussion of its habitability moot. When you combine all these elements, the deadly radiation, the continuous erosion of its atmosphere, the extreme climate caused by tidal locking, and its probable lack of water from the start, the picture that emerges is decidedly grim. Proxima b serves as a powerful illustration of why a planet's position within the habitable zone guarantees very little. It is situated in the correct location, but at an unfortunate time, and orbiting a particularly unsuitable star.
This isn't to say we should dismiss it completely, as the universe often holds surprises. It's conceivable that Proxima b possesses an unusually powerful magnetic field for protection. Perhaps it began with an atmosphere so dense that a remnant still survives after billions of years of stellar assault. Life might even persist deep beneath the surface, shielded from the radiation. But if we assess the situation based on probabilities from our current understanding, the likelihood of discovering an Earth-like world there is vanishingly small. The discovery of this planet became a pivotal lesson for everyone involved in the search for exoplanets, prompting a major reassessment of habitability criteria and a much more critical examination of the parent star's nature. Red dwarfs, once seen as the most promising places to find life, are now regarded with substantial skepticism. It may be that the true nurseries of life are not found around the most common and enduring stars, but rather orbit quieter, more stable ones like our own Sun. The story of Proxima b is one of diminished expectations, yet this makes it no less compelling. In fact, it is transformed into a perfect, natural laboratory for investigating how planets manage to survive, or fail to survive, under the most punishing conditions. And as it turned out, the saga of this system doesn't conclude with just one well-known planet.
Further observations revealed that Proxima b is not suffering alone. It has cosmic sisters.
Proxima b's detection in 2016 was a major achievement for the radial velocity method and permanently altered our view of the Sun's immediate cosmic neighborhood. But science is a process of constant inquiry. A single discovery sparks new questions and drives the quest for more refined observations. Was Proxima b an isolated planet, a lone survivor orbiting a volatile star? Or was it merely the first discovered member of a larger planetary system? To find an answer, astronomers kept a close watch on the Doppler whisper of Proxima Centauri, listening for signals that might betray other, unseen worlds. This endeavor demanded even greater patience and expertise. With the signal from Proxima b already identified, it could be computationally removed from the data. The challenge then became sifting through the remaining noise for even fainter and possibly longer periodic fluctuations that could point to other planets that were either less massive or in more distant orbits. Their dedication paid off. In 2019, a global team of astronomers, led by Mario Damaso from Italy's National Institute for Astrophysics, uncovered something fascinating while analyzing 17 years of data from the HARPS and UVES spectrographs. Alongside the familiar 11-day signal of Proxima b, their analysis showed another extremely faint, long-term cycle. The star appeared to have an additional wobble, with a period of roughly 1907 days, or about 5.2 Earth years. The signal was on the very edge of what could be detected, so the researchers approached it with extreme caution. Its amplitude was even smaller than Proxima b's, meaning it could have been an artifact of other phenomena, like the star's own long-term magnetic activity cycles. To either confirm or deny the presence of a second planet, they needed independent data. It was at this point that another technique, astrometry, came to the forefront. Astrometry is the oldest field of astronomy, focused on making incredibly precise measurements of the positions and movements of celestial objects. While the radial velocity method tracks a star's motion toward or away from us, astrometry charts its minute shifts across the plane of the sky. As a planet orbits its star, its gravitational pull causes the star itself to trace a tiny ellipse against the backdrop of distant stars. Spotting this movement is an immense challenge, but it is precisely the kind of task for which the European Space Agency's Gaia Space Telescope was built. The astronomy team delved into data from the Gaia mission, alongside archival images captured by the Space Telescope over numerous years. While this information was not definitive, it did reveal a clear disturbance in Proxima Centauri's motion, which was consistent with the gravitational influence of a second, more substantial and distant planet. In January 2020, the team formally announced the potential discovery of a planet candidate designated Proxima Centauri c, or simply Proxima c. This newly identified world presented a stark contrast to its inner sibling. Based on the available data, Proxima c is categorized as a super-Earth, or perhaps a mini-Neptune, with its minimum mass estimated to be around 7 times that of our own planet. It circles its star at a considerably greater distance of about 1.5 astronomical units, a separation 1.5 times farther than the Earth is from the Sun. At such a remove from a dim red dwarf, the environment is profoundly different, placing Proxima c far outside the star's habitable zone. The planet receives only about 3 to 4% of the heat that Earth gets from the Sun, making it a frigid, icy world. Its equilibrium temperature, before factoring in any potential greenhouse effect, is calculated to be approximately minus 234 degrees Fahrenheit degrees Celsius, a temperature even colder than the surface of Pluto. The true composition of this planet is still an enigma. With a mass 7 times that of Earth, it sits on the threshold between rocky super-Earths and gaseous mini-Neptunes. It might be a vast rocky planet with an incredibly dense atmosphere, or, more plausibly, a world abundant in ice and other volatile compounds, shrouded in a thick hydrogen and helium envelope, much like our solar system's Neptune or Uranus.
Perhaps the most astonishing part of Proxima C's story is that in 2020, astronomers might have actually laid eyes on it. A research team using the SPSRI spectrograph at the Very Large Telescope in Chile captured a direct image of a faint point of light near Proxima Centauri. The object's location precisely matched the predicted orbit of Proxima C, and if this observation is ultimately verified, it will represent a monumental breakthrough, making it the closest exoplanet to us ever to be directly photographed.
Following this, astronomers kept scrutinizing data from the HARPS spectrograph, applying increasingly sophisticated processing techniques. In 2022, a different team, spearheaded by João Faria from the Institute of Astrophysics and Space Sciences in Portugal, declared the detection of a third signal. This new signal was fainter still than the previous two, suggesting the presence of another planet orbiting even closer to the star than Proxima b.
Designated Proxima Centauri d, this planet was revealed to be a truly minuscule world. Its minimum mass is a mere 1/4 of Earth's, or more precisely 1.25%, which establishes it as one of the least massive exoplanets ever identified through the radial velocity method. To put it in perspective, it is even lighter than Mars, which itself has only about 1/10 the mass of Earth. Proxima d orbits perilously close to its star, completing a full revolution in just 5.12 Earth days. This proximity places it even nearer to the fiery dragon than Proxima b, ensuring it is saturated with even more intense radiation, which leaves no possibility for habitability. In all likelihood, it is a scorched, airless sphere of rock. But its very existence is a remarkable discovery, demonstrating that even the smallest, faintest stars can host entire planetary systems with incredibly diverse configurations.
Let's now consider this planetary family in its entirety. What we observe is an extraordinary, compact, and profoundly alien arrangement that bears no resemblance to our own solar system. Orbiting almost close enough to touch the star is the tiny, scorched world of Proxima d. A bit farther out, within the technical habitable zone, but under relentless assault from stellar flares, is the Earth-sized planet with a tragic destiny, Proxima b. And far beyond, shrouded in icy darkness, orbits the cold giant, Proxima c. This system raises numerous questions for theorists who model planet formation, particularly concerning the origin of Proxima c. It's difficult to explain how a planet with 7 Earth masses could form so far from the star, where the protoplanetary disk would have been extremely thin. One leading hypothesis proposes that it originally formed much closer in, beyond the snowline, and subsequently migrated outward to its present-day distant orbit. The study of this triple system is fundamental to understanding how planets form around the most prevalent type of star in our galaxy. Each of these worlds, Proxima d, b, and c, provides a distinct case for scientific investigation. They are 3 wholly different planets, each shaped by unique conditions, yet all bound to the same highly complex parent star. And so, our unseen stellar neighbor has been revealed to be not just a solitary star, but an entire miniature and bizarre system, brimming with mysteries and paradoxes. It is no longer a simple coordinate on a celestial map. It is a whole family of worlds, each with its own unique story. To unravel these narratives and determine what these planets are made of, whether they possess atmospheres, and what their true conditions are like. We will need increasingly sophisticated instruments and methods.
Our journey to Proxima Centauri has thus far been one of concepts and breakthroughs. I've shared with you what we currently know about the star's nature, its volatile character, and the planets that circle it. But now, let's take a moment to reflect and ask a fundamental question. How do scientists manage to acquire such astonishingly detailed information about an object that, even viewed through a powerful telescope, appears as nothing more than a faint speck of light?
The way we find these answers is a narrative of human innovation, involving the invention of extraordinarily precise instruments and the design of ingenious analytical techniques that let us convert faint starlight into a wealth of information. This is nothing short of a true interstellar detective story, and the primary tool in this investigation, as with all of modern astrophysics, is spectroscopy. While the fundamental concept behind this method is straightforward, its potential applications are practically boundless. When you pass a star's light through a prism or a special device called a diffraction grating, it separates into a spectrum, which is the classic rainbow you learned about in school. If you inspect this spectrum with highly accurate instruments, however, you discover it isn't a continuous band of color. Instead, you'll see it is interrupted by a series of dark, vertical lines, which are known as absorption lines. The origin of these lines was understood back in the 19th century. It turns out that every chemical element, when it's in a gaseous form, absorbs light at very specific and unique wavelengths. As light radiates from a star's intensely hot core through its cooler outer atmosphere, atoms of elements like hydrogen, helium, iron, and calcium intercept their own distinct portions of that light, creating dark gaps in the spectrum that reaches our telescopes. These dark lines effectively act as the chemical fingerprints of the elements present in the star. By carefully analyzing the position and intensity of these spectral lines, we can precisely determine the chemical composition of a star's atmosphere, even when it's light years away. It is through spectroscopy that we know Proxima Centauri, much like our Sun, is composed mostly of hydrogen and helium, with trace amounts of heavier elements mixed in. But that is just scratching the surface of what a star's spectrum can tell us. For instance, the width of these absorption lines can reveal details about the temperature and pressure in the stellar atmosphere. More importantly, a shift in their position, a phenomenon known as the Doppler effect, which I've mentioned before, provides the essential clue for discovering exoplanets. As a star moves closer to us, its entire set of spectral lines shifts towards the blue end of the spectrum. Conversely, as it moves away, the lines shift toward the red end. By measuring these incredibly subtle shifts with high-precision spectrographs, such as the High-Accuracy Radial Velocity Planet Searcher, or HARPS, and its successor, ESPRESSO, at the Very Large Telescope, astronomers successfully detected all 3 planets orbiting Proxima Centauri. The precision of these devices is so extreme that they must be kept in vacuum chambers at a constant temperature. This isolation is necessary to prevent the slightest changes in Earth's atmosphere, or even the thermal expansion of the instrument's own parts from corrupting the delicate measurements. In essence, these are the most perfect and stable thermometers and rulers that humans have ever conceived. Spectroscopy also gives us a window into a star's magnetic activity. A powerful magnetic field produces what is called the Zeeman effect, which causes a single spectral line to split into several very closely spaced components. By measuring this splitting, we can map the magnetic fields on the surface of Proxima Centauri, pinpoint the size and strength of its enormous star spots, and develop a clearer understanding of the physics behind its ferocious flares. Following spectroscopy, the second most vital technique is photometry. On the surface, this method seems simpler. It involves the precise measurement of a star's brightness over time. From these measurements, scientists construct a light curve, which is a graph that plots the changes in the object's luminosity. It was photometry that first exposed Proxima Centauri's volatile nature. On its light curve, stellar flares show up as dramatic, sharp spikes in brightness. By observing the star continuously over many nights, astronomers can compile statistics on these events, their frequency, their energy, and how rapidly they erupt and subside. This information is absolutely critical for evaluating the conditions on the star's planets. This method also forms the foundation of another common technique for finding exoplanets, known as the transit method. If a planet's orbit is oriented just right from our viewpoint, it will pass in front of its star, momentarily blocking a tiny amount of starlight. This event registers as a small, repeating dip on the star's light curve, a technique the Kepler Space Telescope famously used to discover thousands of planets. In the case of Proxima b, scientists searched long and hard for these transits. Finding them would have allowed for an exact measurement of the planet's radius. Combining that with the mass determined from the radial velocity method, we could have calculated its density and confirmed whether it is a rocky planet. Unfortunately, extensive searches, including with the Transiting Exoplanet Survey Satellite, or TESS, have come up empty, suggesting that Proxima b's orbit is likely tilted relative to our line of sight, preventing any transits from occurring. Of course, modern astronomy has advanced well beyond the visible light spectrum. To assemble a complete picture, it's necessary to observe Proxima Centauri across all wavelengths of electromagnetic radiation. In this broader effort, radio telescopes assume a particularly crucial role. Observations in the millimeter and submillimeter wavelengths are especially revealing, and these are conducted by the Atacama Large Millimeter/Submillimeter Array, known as ALMA. Situated on a high-altitude plateau in Chile's Atacama Desert, ALMA is not one telescope, but a massive interferometer, a coordinated network of 66 antennas. These antennas work together to simulate a single telescope up to 16 kilometers in diameter, granting the system an astonishing level of resolving power. It was ALMA that delivered a truly stunning discovery back in 2017. While studying Proxima Centauri, scientists picked up a faint glow emanating from a cloud of cold dust surrounding the star. This glowing material appeared to be arranged in a vast, elongated belt-like structure. This finding was profoundly significant because it suggested that the Proxima Centauri planetary system could be far more complex and richly populated than we had previously imagined. This dust belt may very well be an analog to our own solar system's Kuiper belt, the expansive region beyond Neptune that is home to countless icy bodies. Furthermore, data from the Atacama Large Millimeter/Submillimeter Array, or ALMA, hinted at the potential for a second dust belt, one that is even colder and more remote. This discovery also pointed to a gap between the belts, which could have been carved out by the gravitational pull of another, massive yet undiscovered planet, perhaps a super-Earth or a world similar to Neptune. Such a configuration effectively makes the Proxima Centauri system a miniature version of our own solar system, complete with rocky inner planets and counterparts to our asteroid and Kuiper belts. Analyzing these dust formations gives us priceless insights into the formation and evolution of this entire system. We must also acknowledge the space telescopes that observe in the high-energy parts of the spectrum, like the Chandra X-ray Observatory and the Hubble Space Telescope, which operates in the ultraviolet. These instruments enable us to investigate the most powerful displays of Proxima's temperament, namely its stellar flares and its corona. While Hubble was responsible for capturing that record-setting ultraviolet flare, Chandra is tasked with the continuous observation of the star's X-ray output, which serves as the most reliable measure of its magnetic activity. Ultimately,
Our comprehension of Proxima Centauri stems from a sophisticated fusion of data collected by numerous distinct instruments, positioned in different locations on our planet and in space, each observing across a broad swath of the electromagnetic spectrum. This effort represents a massive scientific collaboration where spectrographs monitor the star's very breath, photometers measure its rhythmic pulse, and radio telescopes uncover the skeletal framework of its planetary system. Every new observation and each new technique contributes another vital piece to this intricate puzzle, which tells a story that does more than just feed our curiosity.
This story also inspires us to take the next audacious leap, to one day make the journey there and witness it all for ourselves. So far, our investigation of Proxima Centauri has been an expedition of light. We've scrutinized photons that have journeyed for 4.2 light-years to deliver news from the closest star system. We have become adept at deciphering these cosmic messages, pulling out details about the star's mass, its temperature, its chemical makeup, and even the presence of planets in its orbit. Yet, a dream resides deep within every researcher and every person who looks up at the night sky. Not merely to watch from a distance, but to actually go there, to traverse the interstellar abyss and see it firsthand.
As our closest neighbor, Proxima Centauri naturally stands as the first and most logical destination for humanity's inaugural interstellar voyage. However, the very term interstellar flight still resonates as something out of science fiction, and for very valid reasons. The distances involved in space are so immense that our minds can barely grasp their scale. Let's try to put it into perspective. The distance to Proxima Centauri is roughly 40 trillion kilometers. The swiftest object humanity has ever launched is the Parker Solar Probe, which reaches a speed of about 192 kilometers per second during its closest pass of the Sun.
Even if we could propel a spacecraft at that phenomenal speed directly toward Proxima Centauri, the trip would require approximately 6,600 years to complete. Consider that for a moment. 6,600 years is a span of time longer than the whole of humanity's recorded history, from the era of the ancient Sumerians right up to today. It is abundantly clear that conventional rocket technologies, which rely on chemical fuels, are entirely inadequate for interstellar journeys. What we require are fundamentally new concepts and technologies that could enable us to achieve speeds that are a significant fraction of the speed of light.
One of the most promising and indeed ambitious of these concepts was articulated within a project whose name seems lifted directly from the pages of a science fiction book, Breakthrough Starshot. On April 12, 2016, which marked the 55th anniversary of Yuri Gagarin's historic spaceflight, the investor and philanthropist Yuri Milner, alongside the legendary theoretical physicist Stephen Hawking, announced the start of this $100 million research and engineering initiative. The program's objective is to prove the viability of an ultra-high-speed, uncrewed mission to the Alpha Centauri system.
The project's core is built around a concept that has circulated for a long time, but had never before received such serious consideration or substantial funding: the idea of a light sail or laser sail.
Picture an exceptionally small spacecraft, a nanocraft no bigger than a postage stamp, with a mass of only a single gram. All the essential systems, a camera, sensors, navigation tools, and a laser for communicating with Earth, are integrated onto this tiny chip, which is called a star chip. This nanocraft is then connected to an incredibly thin and light sail, measuring a few meters in diameter, made from a material that must be extraordinarily durable, lightweight, and highly reflective.
Now let's talk about the most critical element, the propulsion system. In this design, the engine actually stays on Earth, or more precisely, in orbit around it.
It consists of a colossal phased array of thousands of high-power lasers, which can combine their beams into a single, intensely powerful beam, generating up to 100 gigawatts. To give you some context, that amount of power is comparable to the electricity consumption of an entire nation. The plan is to launch a fleet of thousands of these nanocrafts into orbit, at which point the giant laser installation will target the sail of one of them. The immensely powerful beam of light then strikes the sail. As we understand from physics, light is composed of photons, which carry momentum despite having no rest mass. When each photon bounces off the sail's reflective surface, it imparts a minuscule amount of its momentum, creating what is known as light pressure. Under normal conditions, this pressure is practically unnoticeable, but it becomes enormous when a 100 gigawatt beam is focused on the sail. According to the project's calculations, this single pulse of laser light would be sufficient to accelerate the 1-gram nanocraft to a velocity of about 60,000 kilometers per second, which is a staggering 20% of the speed of light. At such a velocity, a trip to the Alpha Centauri system could be completed not in millennia, but in roughly 20 years. A signal transmitted from this probe would then travel back to Earth in a little over 4 additional years. This timeline means that within a single human generation, we could potentially launch an interstellar mission and analyze its findings. Of course, the technological hurdles that must be overcome to make this project a reality are staggering. Each one represents a problem that pushes against or even extends beyond the absolute limits of our current engineering capabilities. First among these is the laser array itself, a challenge of astounding difficulty that involves synchronizing a 100 gigawatt phased array to hold a focused beam on a target only a few meters wide from millions of kilometers away. Next, you have the problem of the sail. It requires a material capable of enduring the immense energy from the laser beam without being vaporized or melted. To prevent absorbing that energy and losing stability, its surface must be exceptionally smooth and reflective. At present, researchers are exploring advanced options like graphene and other dielectric metamaterials. Third on the list is the Starship probe. Compressing all the essential scientific instruments into a crystal that weighs a single gram, while also ensuring they can survive years of intense cosmic radiation, presents a formidable challenge to the field of microelectronics. Then, you must consider the issues of navigation and communication, which are equally daunting. How can we possibly guide a craft moving at such incredible speeds or make any course corrections? More critically, how would we ever retrieve its data? The signal from its minuscule laser transmitter would be almost unimaginably faint after crossing 40 trillion kilometers of space, necessitating a receiving system on Earth nearly as powerful as the laser that launched it in the first place. Finally, there is the fundamental issue of slowing down. The basic mission concept does not include any plan for deceleration upon arrival. This nanocraft is designed to streak through the Alpha Centauri system at 20% of the speed of light, meaning all scientific observation, from planetary photography to data collection, must be accomplished in the few short hours of its flyby. It's an undertaking comparable to trying to photograph one speeding bullet with another. Finally, there is the fundamental issue of slowing down. The basic mission concept does not include any plan for deceleration upon arrival. This nanocraft is designed to streak through the Alpha Centauri system at 20% of the speed of light, meaning all scientific observation, from planetary photography to data collection, must be accomplished in the few short hours of its flyby.
It's an undertaking comparable to trying to photograph one speeding bullet with another. Finally, there is the fundamental issue of slowing down. The basic mission concept does not include any plan for deceleration upon arrival. This nanocraft is designed to streak through the Alpha Centauri system at 20% of the speed of light. Meaning, all scientific observation, from planetary photography to data collection, must be accomplished in the few short hours of its flyby. It's an undertaking comparable to trying to photograph one speeding bullet with another.
Despite this mountain of difficulties, Breakthrough Starshot is far from a mere fantasy. It is a dedicated scientific endeavor that has leading physicists, engineers, and astronomers across the globe working on solutions. The project is already driving the creation of numerous breakthrough technologies in fields like high-powered lasers, advanced nanomaterials, and microelectronics, all of which will have applications far beyond space exploration.
Proxima Centauri and its orbiting planets represent the ultimate target for this theoretical mission. Picture it. 2 decades after its launch, a tiny robotic probe flashes past the planet Proxima b, its camera capturing a rapid series of images. 4 years after that, here on Earth, we would receive the very first detailed picture of a world outside our solar system. From that single transmission, you would be able to discern if the planet has continents and oceans, or clouds swirling in its atmosphere, or if it is merely a desolate sphere of rock. We could potentially distinguish land masses from seas, and even gauge the temperature differences between its day and night sides. Such an image would resolve more questions than a century of our most powerful telescopic observations, transforming an abstract point of data into a real, tangible place. In that moment, Proxima Centauri would cease to be just another invisible star. It would symbolize humanity's first true step out of its cosmic cradle, establishing the first destination on our immense journey to the stars. And though this initial step would be taken by a tiny, gram-scale robot, it would represent a monumental leap for all humankind. Our exploration began with a straightforward, almost childlike question. Why is it that we cannot see the star that is closest to us? This simple query unspooled a whole series of discoveries, each one more intricate and astounding than the last. We progressed from the basic fact of its dimness to grasping the complex thermonuclear processes that power the hearts of stars. You saw how the mass of a star dictates its entire destiny, shaping some into brilliant but ephemeral giants, and others into modest, almost ageless survivors. We came to understand that our own eyesight provides only a narrow sliver of reality, and that in the invisible spectrum of infrared light, our quiet neighbor actually shines as a brilliant beacon. We also uncovered its most unsettling secret, that beneath a calm exterior lies a volatile and ferocious nature, capable of incinerating any world that orbits too closely. We witnessed the discovery of a complete planetary system around this stellar furnace, a family that includes a scorched inner dwarf, a world the size of Earth with a tragic history, and a remote, frozen giant. You saw the ingenious tools and methods humanity developed to detect the faintest stellar whispers across the void of space. Finally, we peered into the future to behold an audacious dream, the interstellar flight project that could one day make this distant point a reachable destination. Now, as we conclude this journey, let's pull all these threads together and ask what the story of Proxima Centauri has really taught us. I think it has offered several profound lessons, but the most significant is a lesson in cosmic humility. As humans, we have a natural tendency toward anthropocentrism, an inclination to view ourselves and our own world as the standard by which all else is measured. To us,
Our Sun appears to be a typical star, and our Earth a standard planet. The tale of Proxima Centauri, however, reveals just how mistaken this viewpoint is. It turns out that the truly normal stars in the cosmos are not yellow dwarfs like our Sun, but rather the faint and invisible red dwarfs that constitute the vast majority of the stellar population. Our own solar system, with its single star and stable, widely spaced planets, might very well be the exception rather than the cosmic rule. It is possible that the most common planetary systems are compact, peculiar, and, by our definitions, completely inhospitable. Proxima Centauri compels us to accept that the most fundamental and widespread processes in the universe are not always the most spectacular or immediately apparent to us. While the explosions of rare, massive stars as supernovae are cosmic announcements, it's the steady, quiet glow of billions of red dwarfs that truly shapes the ultimate destiny of galaxies. Our search for life has centered on stars similar to our Sun, yet it's possible that life exists in environments we can't even conceive of, or maybe it's an exceptionally delicate and uncommon occurrence that demands a precise combination of factors, like a consistent star, a shielding magnetic field, and a very specific orbital distance. A second takeaway concerns the boundaries of your own perception. You don't see Proxima Centauri simply because your eyes are not equipped to detect it, not because it isn't there. This fundamental principle applies across the entirety of science. You cannot directly observe elementary particles, dark matter, or gravitational waves, but humanity has devised artificial senses, from detectors and telescopes to spectrographs, that broaden our awareness and grant us access to these hidden realms. The entire story of human knowledge is a chronicle of transcending our biological constraints, and our unseen neighbor, Proxima Centauri, serves as a powerful emblem of this unending journey. The third lesson brings our attention to the delicate nature of our own planet. When you examine the hostile environment of Proxima b, you gain a renewed appreciation for the extraordinary circumstances enabling life on Earth. Our consistent sun, a robust magnetic field that shields our atmosphere, and a moon that keeps our planet's axial tilt steady. None of these elements were guaranteed. They are the product of an incredibly lucky cosmic lottery. By considering the radiation-blasted wasteland that likely defines our closest planetary neighbor, you develop a much deeper sense of how priceless and fragile our own pale blue dot truly is. The saga of Proxima Centauri is nowhere near its conclusion. In reality, it's just getting started. With its unparalleled sensitivity, the James Webb Space Telescope is already focused on this star system. It's possible that within the next few years, it might successfully analyze light filtered through the atmosphere of Proxima b, assuming one exists, and provide the first-ever insights into its chemical makeup. It's conceivable that later generations of telescopes could capture direct images of all three planets and create detailed maps, or perhaps even the dream of a Starshot initiative will materialize one day, sending miniature probes from Earth to journey through that distant system. You have to wonder what other mysteries this silent neighbor is keeping from us. Could there be additional planets orbiting the star? Might there be frozen moons similar to Europa or Enceladus, harboring oceans beneath their icy crusts? The solutions to these puzzles are something only the future can reveal.